All right, thanks. I sort of lost my voice, so I hope you can hear what I'm saying. As Kristen said, thanks everyone for joining the webinar today. Just before I introduce the speaker, I want to say huge thanks to Caroline for the wonderful job she's done as PSMIP co-chair for the last 2 years. Caroline's energy, ideas, and execution has been obviously invaluable to PSMIP and US CLIVAR, but not to worry though, because she's just been reappointed to the panel for the next 9 years. Just kidding, Caroline. That's just 1 more year. And at the same time, I'd like to welcome incoming co-chair Maria, and thank her for agreeing to take on this role. I certainly count myself lucky to work with people like this. So with that, today we'll be joined by Dr. Ryan Spackman, who will be talking about the NOAA El Nino Rapid Response field campaign. Ryan, who I guess is just down the road from me at the moment, works in NOAA's Earth System Research Laboratory, or ESRL, in the Physical Sciences Division. Ryan received his PhD in Atmospheric Sciences from Harvard. In addition to ENRR, Ryan's been involved in several other notable campaign programs and field campaigns, such as HIPPO, which is flying around from pole to pole like Santa Claus on a G5, as well as CalWater 2015, which we've heard about recently. So Ryan, welcome. We're glad to have you, and please take it from here.
Thanks, Chris, for the kind introduction. Let me know if the sound quality is okay. I'm also losing my voice, so apologies, but we'll figure out a way to get through. So almost a year ago now, we received the green light from NOAA upper management to move forward with the NOAA El Nino Rapid Response Field Campaign. The Physical Sciences Division at the NOAA Earth System Research Lab here in Boulder largely led the planning, execution, and now going into the modeling and analysis phase of the project. But we also closely worked with other colleagues, and I want to make note in particular of 2 line offices that we work very closely with here at NOAA. One is the National Centers for Environmental Prediction, specifically the modeling arm of the National Weather Service, and we also worked closely with NESDIS, the Satellite Data Information Service part of NOAA. And those were 2 very important collaborations. They were involved from the get-go, through the planning and in the execution, the daily decisions that were made in the field. And that's been important from the point of view of ultimately taking what we do well at PSD, which is process studies, and taking it to the end of the spectrum, to the model improvement. And there'll be more I have to say about that, and I would also welcome Randy Dole, who I think is also on the line, to chime in on that during the discussion phase. I had the privilege of working with Randy and the whole ENRR science team. I was primarily involved in this from the planning and execution perspective of ENRR, but I'm also involved in some of the modeling and analysis activities. And the emphasis here is going to be largely on the what we did to make this happen, the execution, and I'm going to hint at where things are going from the process study and model improvement point of view. So I'm going to take you on a tour over the next probably 30 minutes or so. I hope to leave significant time for questions. I want to call attention to an article that I was reading, or I guess it was a piece in Nature magazine published in October 2015. I was on a commercial flight out to Honolulu at the beginning. Randy and I both were on the commercial flight out to Honolulu at the beginning of the field campaign. And there were a couple of interesting programmatic quotes that were in this article. This was the Hunting Godzilla El Nino article in Nature that some of you may be aware of, familiar with. And there was a comment in there by a prominent climate scientist that frankly, government agencies can't do this. They can't respond to an El Nino or a La Nina phenomenon because of the significant lead times required to get the resources in place and move the facilities into the field. And so I was feeling pretty good about this at the beginning of the field campaign, thinking, we're on the way to doing this. And in essence, we planned and executed this effort, ENRR, in less than 6 months, and I would argue it's more like 3 to 4 months, for a complex field experiment that typically takes 2 to 3 years to plan. So I'll have more to say about the details and all that went into that and some of the lessons learned that came out of that process toward the end of the presentation. The overarching goal here was to determine the initial atmospheric response to the 2015 El Nino, and the hard part, its implications for predicting weather, not just along the West Coast, but throughout the contiguous United States. And in a nutshell, we conducted the first field campaign during a very strong El Nino in the sense of going to the heart of the processes, going into the deep tropics and making the observations near the tropical convection, which was largely in the central and eastern tropical Pacific during this event. And distilling down the science, or the objectives, if you will, into two nuggets. First and foremost, we were going after, the goal here was to observe and understand the physical processes, characterizing that first step in the chain, linking the sea surface temperature anomalies to the large-scale convection that then leads to divergent outflow aloft, which then couples into the mid-latitude wave train, producing weather impacts around the globe. The other dimension to this, which was also very important, was from the perspective of how do the observations, what impact do they have on the forecast? And of course, the key point here is that in the deep tropics, south of Hawaii, southeast of Hawaii, this is a very data-sparse region with fairly few commercial aircraft transects. Of course, all those observations are in the upper troposphere anyway, and then everything else is primarily from the satellite perspective, so no vertically resolved observations. And so that was another key goal, was to identify data assimilation and satellite uncertainties and model deficiencies. So ENRR, I don't need to motivate for this audience. Of course, it was one of the 2015-16 event was one of the strongest on record, but of course, this had a different flavor than the 1982, 83, and the 1997-98 events, with a more central Pacific, tropical Pacific Ocean focus in the most recent event. The sea surface temperature anomalies skewed more to the west, south of Hawaii, southeast of Hawaii, with anomalies approaching 2.5 to 3 degrees Celsius. And of course, that has impacts on, or that has an influence on the coupling across the subtropical jet to the mid-latitude wave train with weather impacts downstream. And of course, one of the interesting questions that the community is addressing, and we're certainly interested in here in PSD, is what happened to the Southern California rains? And so that's one of many questions that we hope that these data from ENRR help to address, this unprecedented data set. So programmatically, this ENRR in many ways was rooted in the CalWater effort. And I think there was a former webinar, CLIVAR webinar on this topic, probably in the last round, last year that is, cycle, on CalWater 2. And CalWater 2, in a nutshell, was to study the evolution and the structure of atmospheric river events, specifically with impacts along the west coast of the United States. And it's coupling to the deep tropics. But there's another dimension to that, and that was to understand the role that particulate matter, long-range transport of pollution, namely from sources in Asia, dust from the deserts of Asia and further upstream, how they influence or modulate the precipitation associated with these landfalling atmospheric river events along the west coast. So the reason why I mention this and show this conceptual framework, which comes from our white paper, is that this, in many ways, planted the seed for the El Nino rapid response. Many of the programmatic elements, the facilities, were already in a pipeline ready to do science when the El Nino, when it became clear that there was going to be a very strong El Nino, or likely to be a very strong El Nino in the wintertime. And so the way things played out was we were planning to take one of the NOAA aircraft assets, the Gulfstream 4, out to do a test of a new instrument, a wind LiDAR that was being developed. We were going to do validation with Dropsonde from the G4. Well, it turns out the wind LiDAR wasn't ready for deployment, and so it became an available asset. And it didn't take long for us to figure out, and this was in the July-August time frame in 2015, so about 6 months out from when we deployed, that this was a real opportunity to make use of the G4 to go after the heart of the El Nino, if you will. At that time, we were cautiously optimistic about the prospects, and as we continued our strategic discussions into August, and Randy Dole and Robin Webb, our lab director, began to socialize this at upper levels of management within NOAA, it became clear that there was larger buy-in into this corporately across NOAA, and that, well, the number of flight hours that we had on the table, which was in essence 80, the equivalent of about 10 science flights, maybe wasn't enough to do the science that we really wanted to go after. And so suddenly this morphed into a reallocation. So this is getting into some of the programmatic details, but an important aspect of the rapid response in trying to figure out how to reprogram resources, if you will, on short time scales within the organization. And in parallel with that, there was an initiative, which I'm sure Randy could tell you a whole lot more about, the development of what was a Tiger team with representation across all the various line offices of NOAA, so including the National Weather Service, NESDIS, the Office of Marine and Aviation Operations that handles the deployment of facilities. And there was a larger discussion there about what the nature of this rapid response would be. And so there were some lessons learned that came out of that too, because when you're trying to pull something like this off on short time scales, and you're waiting on decisions at the upper level, there were some discontinuities there in terms of making everything click. And given the complexity of this and taking the aircraft, as I'll go into more detail, into it was from Hawaii wasn't so much of an issue, but we were looking at potentially a foreign deployment to other island sites. There are agreements involved. So there were a lot of lessons learned throughout that process. So the focus here, ENRR, was at least in the Calwater context, was at these linkages between the deep tropics and the extratropics, with that examining the initial atmospheric response to the deep convection from the sea surface temperature anomalies, and then examining those linkages, and I'll show you the strategy for how we plan to tackle that from the divergent outflow from convection into the mid-latitudes. And so this is my best attempt so far at trying to render these processes in a conceptual framework, if you will. And so take this with a grain of salt. This is a work in progress, something that we're looking to work into the mission paper that Randy Dole is leading on ENRR. And so again, the two questions here, emphasis on processes. How well do models represent the tropical atmosphere's response to El Nino, and looking at that first step in the cascade of processes from the deep tropics into the mid-latitudes. And that's represented here in this oval encircling tropical convection. These gray blobs are meant to represent large-scale convection on the scale of 500 to 1,000 kilometers in zonal extent. With divergent outflow, these thick black arrows are meant to represent outflow at the highest altitudes in the tropical troposphere, below the tropical tropopause layers, so nominally 200 millibars or so of pressure. And then I tried to represent here the process of the influence or interaction with the subtropical jet, so the strengthening and the extension to the east of the subtropical jet with impacts downstream. An exact orientation of this isn't, don't read into that, but that's the general concept. And the other part to this, of course, is the impact of the observations. To what extent do they, the observations near the convection, so in these regions, this data sparse region, have an impact on forecast metrics, specifically in the continental United States. Okay, so now drilling down into the field campaign itself. So we completed a pretty tall agenda here, in my view, given the time scale we had to pull it all together. It happened over the January to March 2016 time period. We had 22 science flights with the NOAA Gulfstream 4 research aircraft. That's the high flyer reconnaissance Hurricane Hunter that NOAA has for doing typically hurricane reconnaissance, all from high altitude, dropping the sondes through the events. We had the aircraft was deployed for about almost 2 months, from late January into mid-March. We operated completely from Honolulu, and that was a blessing for sure. There's more to say about that, and I'll touch on that in a few minutes. And the goal here was to go right after the heart of El Nino, so to go right where the convection was associated with the sea surface temperature anomalies. And from the Hawaii perspective, we primarily had to operate north of the equator. And so the question there going in was, well, is the large-scale convection going to largely stay north of the equator? And based on historical data from the 97, 98, the 82, 83 El Ninos, going into February, we expected the convection actually might tail further to the south of the equator, in which case we wouldn't be able to get to it. It's about 2.5 hours to get on station from Hawaii to where most of this convection was. So you end up spending over 50% of your flight, typically 7 to 8 hours in duration, to get to your science. And so that we would have had very little on-station time to do our science. Primary payload here were dropsondes, about on average 30 per flight, depending on what the particular emphasis of that flight was. And we also had a tail Doppler radar on board, and we got better about using that over time, and I'll show a few examples of how those data could be used to further our understanding. The Global Hawk, just pictured here, was also part of the equation. It was supported by the NOAA Unmanned Aircraft System SHOUT program, Sensing Hazards with Operational Unmanned Technology. The emphasis of SHOUT was on forecast improvement. To what extent do observations in data sparse regions or in targeted regions have an impact on the forecast downstream? And they've been doing a number of hurricane reconnaissance efforts associated with targeted observations, but they didn't have any plans to necessarily participate in CalWater efforts, but given the emphasis, the NOAA-wide emphasis on the El Nino Rapid Response, it became clear that they would add a tremendous amount of value to the effort. And I'll explain that in a little more detail in the next graphic, and how that plugs into or how that syncs up with the Gulfstream 4 strategy. Keep in mind the Global Hawk can fly for 24 hours at a time. They did 3 research flights. There's tremendous capability there, and that was all done during February. We also had 2 radio sonde campaigns, one from Christmas Island for about 2 months duration. Christmas is due south of Hawaii. It's about 2 degrees north latitude. It's literally at the epicenter of the 2015-2016 El Nino. And we did twice daily at synoptic time launches from there. We also had an opportunity, a piggyback opportunity, on the NOAA Ron Brown, which was going to be doing a tropical atmosphere ocean survey, a TAO survey, from Honolulu to San Diego from mid-Feb to mid-March. And they were cruising down 2 lines of longitude between 8 north and 8 south, and we did up to 8 times daily radio sondes from the ship. And they were in, as you can see in this graphic, in a data sparse region of the eastern tropical Pacific. So this graphic is a plan view the implementation strategy. And in the upper right-hand corner, I want to call your attention to the campaign timeline here. It's probably a little hard to read, at least it is on my screen. You can see the Gulfstream 4 was out for an extended period, almost 2 months, to kick off the campaign, and the Christmas Island observations started in earnest in late January through the end of March. And then we had NASA Global Hawk activity participation in the month of February, and the Ron Brown, its TAO survey from mid-Feb to mid-March. The other facility that's not explicitly included here, we did have some coordination with another aircraft effort. The Air Force reconnaissance C-130Js were out in the Eastern Pacific during this time period, namely February, and their emphasis was more on atmospheric river activity and potential influence from El Nino during that. So they had a total of 6 flights, largely between Hawaii and the West Coast, and the primary payload there were Dropsondes. So the G4, Gulfstream 4, was primarily focused in the deep tropics and due south of Honolulu, and Christmas Island was part of that general theater of operations. We couldn't go much further south than the equator. The focus here was on divergent outflow from the large-scale convection, which was on any given day was almost always in this box, sometimes further to the south and west, sometimes to the southeast, and ideally immediately south. And so a lot of our flight planning decisions were made on the proximity of that, of the convection. And we also had put plans into place to potentially take the aircraft to Tahiti and American Samoa, which I'm more or less indicating on my screen here. Tahiti southeast of Hawaii in the southern hemisphere, about 17 south, American Samoa at 14 south, southwest of Hawaii. And there was a lot that went into that because we strongly felt going into this we might not be able to get to the convection from Hawaii alone. Turns out we didn't have to push that button, which is wonderful. The Global Hawk strategy was primarily to focus on the mid-latitudes and subtropics, and there was a coordination effort here in the sense of trying to examine or study, observe the cascade or the chain of events between what was happening in the G4's domain with outflow from convection to the connections or linkages to what was happening in mid-latitudes. And to be honest, I'm not sure how well that worked. That's still a work in progress, but that was the concept at least. And we're also working pretty closely with the C-130 activity to see if we can coordinate with them during the field effort. So a lot of moving parts here. And then Christmas Island is depicted here with the twice daily radiosondes, and there's the Ron Brown legs at 140 west and 125 west. I also want to give you a brief sense of what the Meridional perspective was on this. This is an isentropic framework looking at a slice from the equator to the pole, showing you where the G4 was primarily operating and where the Global Hawk GH was primarily operating. And from the perspective of outflow aloft with at least the upper level detrainment occurring at about the flight ceiling altitudes of the G4, we weren't sure to what extent we were going to capture all that outflow. And we know we captured some, but I'm sure we didn't capture all, and there are ways around that in terms of the analysis. But the idea here was that the Global Hawk could help to fill in that gap with the Global Hawk ceiling between 55 and 65,000 feet. Now in practice, again, that didn't work out exactly according to plan, but that in theory, I think would have been a good strategy for being able to close that loop or to close that gap. Okay, so turning to some of the more mechanics of the actual field effort, the implementation phase, there was a lot that went into this. And in many ways, the anchor for much of this were our daily, 53 days in a row, ENRR science team briefings. They were hosted in Boulder, and the crew in Hawaii dialed in every day. Randy and I were in the field for much of this. And the first thing that I did when I woke up at 4:30 in the morning was I got in the habit of looking at the GOES imagery. And you probably can't figure out where things are here. I'm pointing toward Hawaii. These are 10-degree latitude increments. So the equator is right here, and on every day there was convection. And this is actually, the convection is pretty far to the south and west. I don't remember exactly what day this was. I'm guessing we would not have flown, wouldn't have been able to reach the convection. So, and the reason I'm mentioning this is because there was a good tussle that was going on during the course of this field campaign. These were daily briefings that were supposed to inform what we were doing with the Gulfstream 4 aircraft and also informing what the Global Hawk was doing. And these were actually, in many ways, research seminar oriented too. There was a lot of good scientific debate that went on here about to what extent the model input was providing real useful information. And over time we came, or at least I came to the opinion that, well, we had to base a lot of our decisions based on satellite imagery, but we were looking at this 12 hours before the plane would actually get there. And because it was a diurnal cycle and convection, it was very challenging to get a feeling for where we were going to put that aircraft. And at the end of the day, it turned out to be a lot of dynamic flight planning. And for those who have done airborne science, that's not an ideal scenario, and depending on your pilots and crew, it can be a pretty challenging endeavor. And we had a wonderful crew working with us and understanding the circumstances which we were dealing with, and we were able to accommodate it. We went into each flight with as many as, we had a core plan, and then we had a plan A and a plan B, which we could quickly send off to air traffic control if we felt like one wasn't going to work versus the other. The NOAA Ron Brown crew wasn't able to plug into these on a daily basis like we were, but they were on more of a pre-programmed schedule, but we were in close coordination with them, conversation with them, and did a few coordination drops from the G4 when they were doing upsondes. We got some good comparisons there, and of course the twice daily radiosonde launches from Christmas. This is what we actually accomplished. There are 4 different field activities which are represented in this graphic. The NOAA Gulfstream 4 are the first 3 colored traces here, with most of our flights south of Hawaii, with 2 different sampling strategies here. One was enclosure, a closure module, if you will, around large-scale convection. Turns out that was a very challenging endeavor and took us a while to figure out how to do that in a thoughtful way from the scientific perspective, but also, of course, keeping safety in mind. And that was so that was something that we were able to accomplish, and then make better use of the tail Doppler radar, which could paint precipitation if we were able to fly around the convection, and added additional information about the wind environment around this large-scale convection. The other sampling strategy was to fly north of the convection, and that's what these long survey, east-west zonal surveys are. There was oftentimes convection to the immediate south, or a couple degrees to the south, and we were looking at large-scale processes there. And in many cases, we would observe winds, southerly winds along those legs that were up to a factor of 2 higher than what the GFS, for instance, was suggesting they would be. So an interesting preliminary result. The other trace here from the Gulfstream 4 is a series of 3 flights over 6 days to track the development of an atmospheric river through a tropical moisture export event associated with large-scale convection to the south, a budget box analysis across an atmospheric river on day 3 or day 4, I guess it would be, and then the last day of the sequence, science and transit on March 10th back to the west coast of the United States. So some interesting science from that sequence as well. NASA Global Hawk are the dash traces, primarily operating in the mid-latitudes and in the subtropics, in coordination with what we were doing with the G4. And lastly, the Ron Brown here, the fainter yellow trace here, out to a point along 140 west, about 9 north, and then due south into the southern hemisphere, and then coming back along 125 before going into San Diego. And from the Ron Brown, 193 radiosondes were launched over the course of that, up to 8 times daily along these north-south legs in the deep tropics. Christmas, again, due south of Hawaii, 124 sondes over the course of the deployment, twice daily. And from the aircraft assets, we deployed over 625 sondes in the 22 research flights that we performed over the period. 90 sondes from the Global Hawk. There were some challenges with the Global Hawk. The Dropsonde system on board that aircraft, so we didn't get nearly as much data from the Global Hawk as we would have liked. Capability-wise, it can actually launch 90 sondes in a given flight. So it's tremendous capability. And I should also mention there were two other payloads on board the Global Hawk, a microwave sounder from NASA JPL, and also a KU-Ka band radar from NASA Goddard called HIRAP. So there's additional data there that could potentially be used. A lot of coordination between the platforms, and this went on the side, separate from the daily briefing. So there was a sequence of events that happened every day that started as early as 6:30 in Hawaii to coordinate all these assets across the theater of operations. And I'll tell you about the Alpha Jet here in a separate slide in a minute. So I wanted to give you a feeling for what the data look like, and I don't want to run too long here because I do want to allow time for questions, so I'll go through some of these rather quickly. This is for what we called our convective closure module with the Gulfstream 4, and so this is about half of the flights that we did. And you might be able to make out here the general flight plan, which is the reddish trace. So it's coming south out of Hawaii. This is large-scale convection, over several degrees here of longitude, a few degrees of latitude. And the aircraft was planned to fly this rectangular pattern around it. Well, what the pilot actually did in consultation with the science team in real time, using this mission tool suite real-time mission monitor that we were using, was fly or hug the convection so that we got useful data from the tail Doppler radar, doing dropsondes around the circuit. And I should also mention that these data, the dropsondes, are processed in real time on board the Gulfstream 4 and then sent to the GTS from the aircraft, so they're available for the numerical weather models to use. And many of these data, most of these data, were ingested into the 0Z runs every day. So that's going to be, that's an important part of important aspect of the post-mission analysis that's ongoing. So comparing profiles, this is the left profile here in the deep subtropics, or in the subtropics. Notice the very deep dry layer. There is a dry bias here that has not been corrected. Don't worry too much about that. Those have been corrected, and it really doesn't change the, at least qualitatively, what this looks like. It is very dry from about 800 millibars up in that region. We saw this day in and day out as we passed through the subtropics, getting to our on-station science area. This is a moist profile, which is south of the convection, giving you a feeling for what that looks like. And you can see there's winds from the east-northeast here, presumably associated with the convection, and this is outflow aloft. Now, looking at what these look like for a typical outflow module, which is the other half of the flights that we did, flying north of convection. This was a fairly benign day with convection to the south. There's a lot of variability too associated with the diurnal cycle, and so this is probably, when I took this screenshot, it's probably a weaker phase, but there was convection here, significant convection to the south. You can see the tremendous structure here in the moisture profile, with alternating moist and dry layers through the column, and that's L's for left. So in the drier part of this overall flight pattern, but in the more moist pattern, closer to the convection, more moisture, but still quite a bit of structure involved. This is great for testing models and understanding processes, and that's something that's ongoing. So I also wanted to call attention to a coordination effort with the Alpha Jet, which is an aircraft that's based at NASA Ames Research Center, which is in the South Bay Area. It's an aircraft that's operated by H211. That's a company that has an agreement with Google. There's also an agreement with NASA Ames to operate it to do some science. It's not the most practical aircraft to do our science from, but we've been trying to make use of it because it's basically a free asset. It's available for doing science at no cost. except for the people involved, of course. So we coordinated with them on our science and transit back from Hawaii to the West Coast, where we were sampling the atmospheric river. You kind of make it out here from the visible satellite perspective. This is a screenshot that I took while the Gulf Stream 4 was on its way back. That's the green indication there. So shortly after the Gulf Stream 4 took off from Hawaii, the Alpha Jet took off from the West Coast and flew about the time that the atmospheric river was making landfall. This is the radar imagery along the coast. The scale here between, this is the South Bay area. It's probably really hard to make out, but this is the aircraft trace. It's just flying off the coast about 10-15 miles and doing a stacked orientation between 8,000 feet and about 1,000 feet. And keep in mind, these conditions are not ideal. It's all IFR, instrument flight rule conditions. So this was an exciting flight. So understanding what was going on in the synoptic scale from the G4, but then looking at more mesoscale processes associated with the Alpha Jet. And these are also very useful data from a process studies point of view. The payload on the Alpha Jet, of course we had meteorological instrumentation on board, but there's also trace gas measurements, and that's something that can be useful for understanding outflow of pollution from the continent out over the ocean and vice versa. So I also want to call your attention to a capability we had during the field campaign. This is a collaboration with NESDIS and to some extent INSEP in retrievals of moisture and temperature from two instruments on board SUMI MPP, the ATMS instrument with microwave only, and then the CRIS instrument and infrared sounder in combination with the microwave sounder. And what's shown here in the lower left-hand corner are plan views of total precipitable water, integrated water vapor, for several passes of the MPP satellite over the region. And again, it's probably really hard to make out here. This is the flight track, and there are actually times indicated with respect the time offset from the overpass. And so for one particular dropsonde, this one here I'm indicating at the vertex as the plane was coming southeast out of Hawaii, there's comparison here between the retrieved products from ATMS, which is the microwave only, and from CRIS plus ATMS, which is the red trace, in comparison with the dropsonde itself and with the GFS. And the observations in black here show very significant dry layers at the lower altitudes, which the satellite retrievals and the model don't pick up to that extent. And so this is an example of how these observations can potentially make a difference in the forecast, and will help us better understand the processes involved so we can better describe the physics. So in the last few slides here, I wanted to give you a flavor or feeling for how these observations made a difference to the forecast. And there's a much more detailed analysis that's ongoing right now, but we had the opportunity to work with the GMAO group at NASA Goddard because they already produced some of these metrics from the GEOS-5 model. And so what I'm showing here is the 24-hour forecast error as measured by global total moist energy. And I want to specifically acknowledge Ron Gilero at NASA GMAO and also Gil Campo here in our lab, who have worked very closely together during the course of the campaign and continue to work closely together in looking at this in more detail. And so the upshot of the left-hand figure, all the dropsonde data from ENRR from 22 January to 11 March are included here, and there is a negative is good. There's forecast improvement. That's what that indicates. That there's a significant reduction in forecast, 24-hour forecast error, likely due to our dropsonde observations in south of Hawaii. So that's a pretty interesting remark. Now there's kind of mixed results to the north and east, which is interesting, and I don't know that any of us really have an explanation for that. And I'm not exactly sure what data are going into this, probably from the Global Hawk. Actually, no, not from the Global Hawk, because those data are not ingested in real time, but they are from the G4. But it may be some data from the C-130s, which are ingested in real time. So that's a work in progress. From the radiosonde perspective, you can see where Christmas Island is here, big blue dot, which presumably is making an impact. And then you can also see the Ron Brown Tau survey with up to 8 times daily radiosonde launches. And the other note here is that I'm not going to show the graphic here, but given all the observations that we have around the globe, of those taken between 20 north and 20 south, the ENRR dropsondes, okay, that's from the G4, have the greatest contributions to reducing the error on a per observation basis, which is a pretty big statement, given all the other observations that go in are assimilated into the models. Okay, and there's the G4 region. Okay, I want to call your attention to the ENRR data portal. This is our main ENRR webpage, which you can find very quickly if you Google NOAA ENRR. And if you drill down one layer to the data portal, you can find for each of the facilities, from the Gulfstream 4, the Global Hawk, the Ron Brown. We also had a radar, which is off the west coast, the Christmas Island OBS. You can find all the details on the data and download it from there. All the dropsonde data are finalized, quality controlled. Those are all available in text format. There's also tail Doppler radar from the G4, although that's in a less friendly format, which would require more digestion. And the other data sets are in process of being put there and largely finalized. And you can see when you drill down one of these layers what it looks like with all the different observations. Okay, in the last 2 slides, I wanted to hit on a couple of overarching comments. So first and foremost is we pulled it off. We were able to accomplish a rapid response based on information we had in the July-August timeframe. And yes, there were some real programmatic challenges in the sense that we didn't actually get the green light on this literally until a couple weeks before we went into the field. Of course, everything else had to be in motion anyway, and we had to get approvals for everything from an international agreement to operating in Kiribati to diplomatic clearances for the G4 to go into Tahiti. All of our ducks had to be in a row before doing this. So one of the things that we would like to see in the lesson learned context is to be able to build these partnerships more broadly. This was very much of a NOAA effort. Randy and I spent quite a bit of time reaching out, and at the end of the day, were constrained because we had to pull it off, and we just didn't have the time to be able to build those relationships in the way that we would have wanted to. And so that's something that can be done. You can build up those organizations that help to establish a foundation for a future rapid response. And that can be done interagency, it can be done with other academic partners, through industry, and it can be working within various government agencies to make sure the facilities are available to be able to accommodate, the instruments are ready to go to be able to make those observations. So it's part of a larger rapid response initiative that I would like to see play out in the future. ENRR was a highly successful field campaign. Tremendous amount of observations. These are data that are going to be looked at for years to come. And one of the things I wanted to call attention to is the fact that we had integration across the entire spectrum of capabilities, from making the observations to the climate science, to forecast modeling improvement, to the folks in the field, the engineers that made it happen. It was that integration at the level of planning and execution that made a real difference, and it's going to make a difference in terms of the use of these data going forward and the analysis of these data. And I can comment more about that in the question session. And so that kind of touches on this last point here is, you want to bring that entire team together to be able to maximize your science, and ultimately that leads to model development and improvement of future prediction systems. Okay, and so this is summarizing some of the next steps and future directions, and there's a lot more to be done, and we're just starting to crack the code on the data that we took during ENRR. But there's potential here for future studies, and hearing from our partners in the more operational arms of NOAA, they would be interested in working with us more closely going forward. And so, although this may be a little provocative, because outcomes we're still in process here, but they may justify longer-term atmospheric and oceanic observations in these data-sparse tropical regions to look at air-sea interactions, large-scale convection, and coupling to mid-latitude processes for varying endomodes and as modulated by the MJO. Of course, we're very interested also in to what extent these observations may make a difference in reducing the forecast error in 1 to 7 day forecasts, and that's an ongoing effort. And how would that drive the observing strategy? And of course, this is another important point in partnership with the Satellite and Data Information Service is using these measurements to improve our algorithms to add additional input into model forecasts. And I'm going to stop there in the interest of time, and thank you for your attention.